Place your hand on the nearest solid thing, a desk, a wall, the side of a chair. For a moment, do not think of it as furniture. Think of it as a claim. Your fingers press down, the surface pushes back, and your nervous system reports something so obvious that it seems beyond argument. Matter is made of stuff. It has weight because tiny things inside it have weight. It is solid because tiny things inside it are solid. The world holds together because the smallest pieces are like miniature stones, stacked into larger stones, stacked into bodies, planets, stars, and everything that can be touched. That is the picture almost all of us inherit. It is not foolish. It works well enough for a hammer, a bridge, a human hand. But it begins to fail the moment we ask where the weight of that hand actually comes from. Not where the atoms are, not what elements they contain. The deeper question is stranger. Why does any of it weigh anything at all? What makes a proton, the tiny positive heart of almost every atom in your body, resist acceleration, bend under gravity, and give ordinary matter its mass? The answer sounds like a contradiction. The proton is not heavy because it contains heavy ingredients. The ingredients are almost weightless compared with the proton itself. The mass is mostly not in the particles. It is in the valence between them. It is in motion, confinement, quantum fields, and the energy of the strongest force in nature trapped inside a space smaller than a trillionth of a millimeter. The thing that feels solid under your hand is, at its deepest accessible level, not a pile of little solid beads. It is a disciplined storm. This is the uncomfortable thesis of the story. Matter is real, but our intuition about why it is real is wrong. The solidity of the world is not the solidity of tiny bricks. It is the stability of patterns. The mass of the world is not mainly the inventory of tiny, massive parts. It is the stored energy of interactions. And the most familiar word in physics, mass, turns out to be less like a substance than like a negotiated outcome. A number produced when quantum fields are forced into a small region and cannot escape. There is a counter-argument that deserves to be taken seriously. If your hand cannot pass through the table, if a falling rock can crush bone, if a planet can pull an ocean into tides, then calling matter a storm can sound like wordplay. The table is not an illusion. The rock is not imaginary. You cannot philosophize your way through a wall. Physics does not make the world less real. It makes reality less simple. The point is not that matter is fake. The point is that reality, at the scale of protons, does not resemble the picture our bodies evolved to understand. The wall is real because the fields are real. The weight is real because energy gravitates. The resistance is real because forces do work. But the small, solid, heavy object you imagine at the bottom of everything is not there. To see why, we have to follow matter down through every layer that once looked final. We have to watch the atom become divisible, the nucleus become structured, the proton become a composite object, and the composite object become a storm of quarks and gluons whose mass cannot be understood by adding up its parts. We have to pass through the Higgs field without giving it more credit than it deserves. We have to enter quantum chromodynamics, the theory of color charge, confinement, and asymptotic freedom. And then, at the center, we have to face the fact that the most ordinary thing in your body is one of the most difficult objects in physics to calculate from first principles. The proton is everywhere. It is inside the hydrogen that fills the stars. It is inside the oxygen you breathe, the carbon in your muscles, the calcium in your bones, the iron in your blood. It is the identity marker of the elements themselves. Change the number of protons in a nucleus, and oxygen becomes nitrogen, carbon becomes boron, gold becomes platinum. The proton is the alphabetic letter from which chemistry begins, yet the letter is not simple. It is written in a language of fields, symmetries, and energy so violent that even our best equations require supercomputers to follow it. The story begins with a mistake that was also a triumph. Long before laboratories could split atoms or accelerate particles, ancient thinkers asked what would happen if you kept cutting a piece of matter into smaller and smaller parts. At some point, Leucippus and Democritus imagined the knife would reach something that could not be cut. An atom, from the Greek for the uncuttable. They were wrong about the details and right about the ambition. They guessed that ordinary matter is not continuous paced, but discrete structure. The world is built from units. The arrangement of the units changes the object. For more than 2,000 years, that idea waited in the background. It returned with chemical precision in the work of John Dalton. Dalton noticed that elements combine in fixed ratios. Water does not take any amount of hydrogen and oxygen it wishes. Carbon dioxide does not choose its proportions freely. The numbers are stable because matter is assembled from countable units. One atom combines with another. Chemical reactions rearrange what already exists. Dalton gave chemistry a particle foundation, and for a while it seemed that the atom had reclaimed its ancient title. The atom was the indivisible unit, the final bead, but final beads have a habit of cracking. In 1897, J.J. Thomson studied cathode rays and found particles much smaller than atoms, negatively charged and identical no matter what metal the instrument used. The electron had entered the world. The atom was no longer indivisible. Thomson imagined a sphere of positive charge with electrons embedded in it, a soft positive pudding carrying tiny negative raisins. It was a reasonable model for a few years, and then gold destroyed it. Ernest Rutherford and his colleagues aimed alpha particles at a thin sheet of gold foil. Most passed through, as if the atom were nearly empty, but a small number bounced back at impossible angles, as if they had struck something dense and concentrated. Rutherford later compared it to firing a shell at tissue paper and watching it return. The atom was not a soft, diffuse sphere. Nearly all of its mass and positive charge was packed into a tiny nucleus. Around it, far away by atomic standards, the electrons occupied a vast region of empty space. This is the first betrayal of touch. Matter feels continuous because your hand and the surface exchange electromagnetic resistance, but the atom itself is mostly emptiness. If an atom were enlarged until its nucleus were the size of a small marble, the electron cloud would extend across a stadium. The ordinary object under your palm is not filled with substance. It is patterned emptiness held together by force. It feels solid, not because its atoms are full, but because electric fields do not allow your electron clouds and the table's electron clouds to overlap freely. Yet the nucleus was not the bottom either. Rutherford identified the proton as the positively charged component of the nucleus. James Chadwick later found the neutron, nearly the same mass as the proton, but electrically neutral. The new picture was elegant. Electrons outside, protons and neutrons inside. Atoms built from a compact nuclear core and a surrounding cloud. The number of protons defined the element. 1 proton meant hydrogen, 2 meant helium, 6 meant carbon, 26 meant iron, 92 meant uranium, The periodic table became a count of positive charges. For a time, the proton looked fundamental. It had a charge, a mass, a role. It was the nucleus of hydrogen and the defining particle of chemical identity. But the proton was already leaving clues that it was not simple. Its magnetic moment did not match the prediction for a point-like particle. Scattering experiments showed that its charge was spread over a small but finite region. The proton had a size. It had internal structure. Something inside it was arranged in a way the old model could not see. Then the particle zoo arrived. Accelerators produced families of short-lived particles that seemed related to protons and neutrons, but were heavier, stranger, and unstable. If every one of them were fundamental, nature had become unnecessarily crowded. Murray Gell-Mann and George Zweig proposed a way to turn the zoo into a grammar. Protons, neutrons, and many other particles were made from smaller objects, quarks. The proton contained 2 up quarks and 1 down quark. The neutron contained 1 up and 2 down. Their fractional charges, strange at first, added to exactly the observed charges, plus 1 for the proton, 0 for the neutron. At first, many physicists treated quarks as mathematical bookkeeping. No one had seen a free quark. No isolated fractional charge had appeared in a detector. But deep inelastic scattering at the Stanford Linear Accelerator Center changed the argument. High-energy electrons fired into protons did not scatter as if the proton were a smooth smear. They bounced from hard, point-like constituents inside. The proton contained smaller, charged centers. The quarks were not merely symbols. They were physical participants in the proton's internal life. But the discovery of quarks did not restore the simple picture. It broke it again. If a proton is made of 2 up quarks and 1 down quark, then perhaps the mass of the proton is just the sum of those quark masses. Smaller weights add into a larger weight. That is the old intuition in a new costume. The numbers refuse. The current masses of the up and down quarks are only a few mega-electron volts each. Add 2 up quarks and 1 down quark, and you get only a tiny fraction of the proton's measured mass, which is about 938 mega-electron volts. Depending on the definitions and scales used, the valence quark masses account for roughly 1%, not 100. This is the central crack. The proton's ingredients, if by ingredients you mean the 3 valence quarks named in the textbook, do not weigh enough to make a proton. The proton is not the sum of 3 small masses. Something else is doing the work. Something is giving the proton almost all of its heft. Not an extra hidden marble. Not a secret heavy core. The missing mass is energy. Here we must be careful, because the language can easily become mystical. Energy is not a ghost substance floating around in place of matter. Energy is a measurable property of physical systems. It can be kinetic, stored in motion. It can be field energy, stored in configurations of force. It can be thermal, electromagnetic, gravitational, or quantum. Einstein's equation does not say matter is imaginary. It says mass and energy are related so intimately that a system's energy contributes to its inertia and gravity. If you trap energy inside a system, the system becomes heavier. This is not metaphor. A box containing light weighs more than the same empty box, because the photons, though individually massless, carry energy and momentum. A hot object is ever so slightly more massive than the same object cold, because thermal energy contributes to the total mass energy of the system. The effect is tiny in daily life, but inside a proton, the energy density is immense. The strong force confines quarks and gluons in a region so small that the energy of their motion and fields becomes the dominant source of mass. To understand that energy, we have to meet the strangest of the fundamental forces. Gravity reaches across the cosmos but is weak between individual particles. Electromagnetism shapes atoms, molecules, chemistry, light, nerves, and touch. The weak force governs certain radioactive decays and the fusion processes that allow stars to shine. But the strong force is the one that holds quarks together, and in a residual form binds protons and neutrons into nuclei. At nuclear distances, it is enormously powerful. Its reach is tiny, about the scale of a proton, but within that reach, it rules. The theory of this force is quantum chromodynamics, QCD. The name sounds like a theory about color, and in a sense it is, but not the color your eyes see. Color charge is the strong force analog of electric charge. Quarks carry color charges, usually labeled red, green, and blue. A proton is color neutral, not because it lacks color charge inside, but because its three quark colors combine into a neutral whole. The labels are metaphors, but the mathematics is not. Color charge is what quarks exchange through gluons, the carrier particles of the strong force. Gluons make QCD difficult in a way electromagnetism is not. Photons carry the electromagnetic force, but photons do not carry electric charge, so light beams mostly pass through one another. Gluons carry color charge themselves. They feel the very force they mediate. They interact with quarks, and they interact with other gluons. The messengers talk to the message. The glue pulls on the glue. From this single fact comes a world of non-linear complexity. Inside a proton, the three valence quarks are not sitting still like beads in a pouch. They are exchanging gluons constantly, changing color, moving relativistically, surrounded by a sea of temporary quark-antiquark pairs generated by the field's energy. The proton is not three objects plus empty space. It is a fluctuating quantum state with valence quarks, C-quarks, gluons, field energy, and correlations that cannot be separated without destroying the object being described. This is where the textbook image becomes actively dangerous. A drawing of a proton as three colored balls is useful for remembering its charge, but it teaches the wrong intuition about its mass. The drawing hides the gluons, and the gluons are not decorative strings. They carry a large share of the proton's momentum and energy. The drawing hides the C-quarks, which appear and disappear through quantum fluctuations. It hides the kinetic violence of confinement. It hides the fact that the number of partons you resolve inside a proton depends on the energy scale at which you probe it. The proton is scale-dependent in a way everyday objects are not. Look at a stone with your eyes, and you see a stone. Use a microscope, and you see grains, cracks, crystals. Use X-rays, and you see atomic arrangements. The stone reveals layers, but the stone is not changing. A proton also reveals layers, but the layers are woven into the energy of the probe itself. At low resolution, the proton may look like three valence quarks. At higher energies, it becomes a crowded sea of gluons and quark-antiquark pairs. The deeper you look, the more populous the storm becomes. This is not a failure of vision. It is a feature of quantum fields. Particles are not tiny permanent pebbles hidden in a bag. They are excitations and interactions in fields, and what you count depends on the scale of the question. This does not mean anything goes. The measurements are precise. The equations are strict, but the object is not classical. It cannot be reduced to a still picture without losing the truth that matters most. Now comes confinement, the rule that keeps quarks trapped. In electromagnetism, the force between opposite charges weakens as you pull them apart. Separate an electron from an atom, and with enough energy, you can have a free electron. But try to pull a quark from a proton, and the strong field resists in a different way. The energy stored in the color field grows as separation increases. The situation is often compared to stretching a rubber band, though the analogy is only partial. Pull harder, store more energy. Eventually, the energy in the field becomes sufficient to create a new quark-antiquark pair. Instead of obtaining a free quark, you obtain new color-neutral particles. Nature will let you rearrange quarks. It will not let you isolate one. Particle accelerators produce jets, cascades of hadrons that spray from high-energy collisions. They do not produce lone quarks drifting into detectors. Every observed final particle is color neutral. This is not because detectors are lazy. It is because confinement is one of the defining features of the strong interaction. Color charge does not appear naked in the world we can observe, yet the same force that confines quarks becomes weaker at very short distances. This is asymptotic freedom, discovered by David Gross, Frank Wilczek, and David Politzer. When quarks are probed at extremely high energies over extremely short distances, they behave almost as if they are free. This explains why deep inelastic scattering could reveal point-like constituents inside the proton. Close up, the quarks can look nearly independent. Pull them apart, and the force tightens into an unbreakable prison. This paradox is one of the great beauties of QCD. Freedom at short range, imprisonment at long range. The proton is a room in which quarks can move almost freely within a small volume, but the walls cannot be broken. That room is not empty. Its walls are energetic. Its air is gluon field. Its floor is a sea of fluctuations. And because of Einstein's relation between energy and mass, the room itself weighs more than the occupants. Here we meet the Higgs field, and we must not turn it into a villain or a savior. The Higgs field is real and essential. Its excitation, the Higgs boson, was discovered at CERN in 2012 by the ATLAS and CMS experiments. The Higgs mechanism gives elementary particles such as electrons and quarks their intrinsic masses through their interactions with the Higgs field. Without those masses, the universe would not have the same atoms, chemistry, stars, or life. The Higgs field matters deeply, but the Higgs field is often misrepresented as the source of all mass. That is not right for ordinary matter. The Higgs field gives the up and down quarks their small current masses and gives the electron its mass. Those values are crucial. Change them, and the neutron-proton balance, nuclear stability, and chemistry can change dramatically. But when we ask why a proton weighs about 938 mega-electron volts, the Higgs contribution through the quark masses is only a small part of the answer. The majority comes from QCD energy, quark kinetic energy, gluon field energy, and the dynamics of the strong interaction. The sharper claim is this: the Higgs field makes the quarks not quite massless, and that fact is vital, but the proton's mass is mostly emergent from strong force dynamics. A physicist would phrase this with more precision than a documentary voice can carry comfortably, but the conceptual distinction is clear. Fundamental particle masses and hadron masses are not the same story. In protons and neutrons, most of the mass is not put in by the Higgs field. It appears from the energy of confined quantum fields. This is why the phrase energy pretending to be matter is powerful but dangerous. It captures something true, but it can mislead if taken too literally. Energy is not wearing a disguise. Matter is one form in which energy and fields behave when arranged in stable patterns. A proton is stable enough to serve as a building block, but its stability is dynamical. It is not the stillness of a stone. It is the steadiness of a tornado that never breaks, because the laws that sustain it never stop. How do we know this? We cannot place a proton on a microscopic scale and watch the energy slosh inside. We infer its structure through scattering, symmetries, conservation laws, and, crucially, calculations. The equations of QCD are known, but they are notoriously hard to solve in the low-energy regime where protons live. The strong force is not small there, so the approximations that work so beautifully in other parts of particle physics fail. You cannot treat the interactions as a tiny correction. The interaction is the object. For this reason, physicists use lattice QCD. They put quark and gluon fields on a discrete grid of space-time points and calculate their behavior numerically. This is not because space-time is necessarily a literal grid in the calculation's physical claim. It is a computational strategy, an approximation that can be refined by making the grid spacing smaller. These calculations are some of the most demanding in science. They use supercomputers to average over enormous numbers of possible field configurations and extract quantities like proton and neutron masses. The achievement is remarkable. Starting from the equations of QCD and the quark masses, lattice calculations reproduce the masses of light hadrons, including the proton and neutron, to high accuracy. This is one of the cleanest confirmations that the proton's mass is not hiding in unknown heavy ingredients. The equations of the strong force themselves, when properly solved, generate the mass. In other words, the storm weighs exactly as much as the measured proton weighs. This is where the story becomes more than particle physics. It becomes a revision of what we mean by stuff. The mass of ordinary matter is not primarily the mass of elementary particles added up like coins. It is mostly the mass energy of confined fields. If you weigh a person, you are weighing QCD. If you weigh a mountain, you are weighing QCD. If you weigh the Earth, the Sun, or a cloud of hydrogen drifting between stars, you are weighing the energy stored in protons and neutrons. There are small corrections, and they matter. Electrons contribute a little. Nuclear binding energy changes the mass of nuclei compared with free protons and neutrons. Chemical binding energy changes mass by even tinier amounts. Thermal energy contributes. Gravity contributes in extreme systems. The universe is not reducible to one sentence. But for the ordinary matter in your body, the dominant source of mass is the same. The dynamics of quarks and gluons inside nucleons. The neutron tells the same story with a twist that makes life possible. A neutron contains one up quark and two down quarks. It is slightly heavier than the proton by about 1.3 mega-electron volts. That tiny difference, small compared with the total nucleon mass, is enormous in consequence. A free neutron decays into a proton, electron, and antineutrino with a lifetime of about 15 minutes. A free proton, as far as experiments can tell, is stable for times vastly longer than the current age of the universe. If the mass difference had gone the other way, if protons were heavier than neutrons, hydrogen might not be stable. A universe full of free neutrons rather than hydrogen atoms would not build chemistry as we know it. Stars would be different, perhaps impossible in familiar form. Water would not be water. Organic molecules would not assemble in the same way. Here, the small Higgs-given differences between up and down quark masses return to center stage. The Higgs contribution may be small in the total mass budget, but its precise values help decide which particles are stable and which worlds can exist. This is the real counterargument to any lazy version of the Higgs is irrelevant claim. The Higgs field is not the main source of your weight, but it is one of the reasons your kind of matter can exist at all. It gives the electron its mass, which shapes atomic size and chemistry. It gives quarks their current masses, which help set the proton-neutron mass difference and the structure of nuclear stability. Calling it a minor player in your bathroom scale weight does not make it minor in the architecture of reality. The proton also connects your body to the first microsecond of cosmic history. In the earliest universe, conditions were too hot for protons and neutrons to exist as stable bound objects. Quarks and gluons formed a quark-gluon plasma, a state in which color charge was not confined into hadrons in the familiar way. As the universe expanded and cooled, the strong force underwent a transition. Quarks and gluons became trapped into protons, neutrons, and other hadrons. The mass of ordinary matter as we know it emerged when QCD energy became locked into stable bound states. Heavy ion colliders have briefly recreated tiny droplets of quark-gluon plasma by smashing nuclei together at tremendous energies. These collisions do not reproduce the entire early universe, but they allow physicists to study matter under conditions where quarks and gluons are deconfined, where the interior logic of protons and neutrons is partially undone. For a fraction of a second so small that language almost fails, the storm is unbottled, then it cools, and the quarks and gluons confine again, forming showers of hadrons. This should change how we think about permanence. The protons in your body are not newly manufactured. Many of them, especially those in hydrogen nuclei, may have persisted since the first moments after the Big Bang. The heavier atoms in your body were forged later in stars and stellar explosions, but the protons themselves belong to a history that reaches back almost to the beginning. Their internal storms have been running for 13.8 billion years. Every breath you take is made possible by objects that have held QCD energy in confinement, since the universe was young enough to be almost unimaginably hot. The stability of protons is not guaranteed by every theory. Grand unified theories often predict that protons can decay, though with lifetimes far beyond any human scale. Experiments such as superchemiocande have searched for proton decay and found none, pushing lower limits to extraordinary timescales. This is not a minor technical detail. If protons are stable, the energy bottled in them may outlast stars, planets, and galaxies. If they eventually decay, then even ordinary matter has a far future death. The question remains open, and that openness is part of the scientific honesty this subject demands. But the proton is not merely old. It is active. Its internal energy matters in stars. The sun shines because nuclear fusion rearranges nucleons into more tightly bound configurations. When hydrogen fuses into helium, the final nucleus has less mass than the separate starting particles. The difference is released as energy. That energy travels outward, scatters through the solar interior, emerges as sunlight, crosses space, warms Earth, drives photosynthesis, shapes weather, and enters the food chain. The light that touches your skin is a message from nuclear binding, a small release of mass energy made possible by the strong force. In this sense, the strong force does not only give matter weight, it also gives stars the ability to pay out energy slowly over billions of years. If nuclear binding energies were different, stars would burn differently. If the strong force were much weaker or stronger, the chain of nucleosynthesis that produces carbon, oxygen, iron, and the rest of the chemical table could change beyond recognition. The proton is not an isolated curiosity. It is a hinge between the microscopic and the cosmic. Now step back to the sensation with which we began. Your hand on a table. That solidity is produced primarily by electromagnetic repulsion between electron clouds, and the electrons are arranged around nuclei whose mass is dominated by protons and neutrons, whose mass is dominated by strong force energy. The table pushes back because quantum fields and forces enforce structure. Your hand cannot pass through because the Pauli exclusion principle, electromagnetic interactions, and the organization of matter prevent the easy overlap of electrons. The table feels simple because your nervous system compresses all of that into pressure. This compression is not a lie. It is a useful interface. You do not need to solve QCD to place a cup on a desk. You do not need to know the proton's part-on distribution functions to walk across a floor. Evolution did not give you a particle accelerator for a hand. It gave you touch, a practical signal. But science exists because the practical signal is not the whole truth. When the mind asks why touch works, it has to leave touch behind and enter equations that no animal sense was built to visualize. The first tension of the documentary is therefore not between science and meaning. It is between two kinds of truth. The table is truly solid for the purposes of life. It is not truly solid in the naive sense of being filled with tiny hard material. The proton is truly a particle in many experimental contexts. It is not truly a particle in the naive sense of being a little ball with 3 smaller balls inside. The quark is truly a constituent of the proton. It is not a constituent you can take out and hold alone. Reality is layered, and each layer has its own language. The danger in popular science is to flatten those layers into slogans. Everything is energy can become empty mysticism. Matter is an illusion can become nonsense. The Higgs gives mass can become a half-truth. The stronger, more accurate claim is more subtle and more powerful. Ordinary matter is stable because quantum fields form long-lived patterns. Its mass is mostly the energy of those patterns, especially the QCD energy inside protons and neutrons. The world is not less real because it is dynamical. It is real because the dynamics are reliable. Reliability is the miracle. A proton is not a quiet object, yet its mass is stable. Its interior is chaotic by human imagination, yet its charge is exactly the charge hydrogen needs. Its fields fluctuate, yet it behaves as a consistent building block across the observable universe. A proton in your body and a proton in a distant galaxy are the same kind of state. They obey the same equations. The storm has a law. That is why chemistry exists. That is why stars exist. That is why science can speak about them at all. There is another counter-argument to consider. If the proton is so complex, can we truly say we understand it? QCD is part of the standard model, and lattice calculations have achieved extraordinary success. But the proton remains an active frontier. Its spin composition, pressure distribution, gluon dynamics, C-quark asymmetries, and three-dimensional internal structure are still being mapped. The future electron-ion collider is designed to probe these questions with new precision. So there is a difference between knowing the core mechanism of mass generation in QCD and having a complete intuitive picture of every internal motion. This distinction matters. Science does not become weak when it admits unfinished work. It becomes trustworthy. We know enough to reject the marble model. We know enough to say that most of the proton's mass arises from QCD dynamics. We know enough to calculate hadron masses from first principles, but we do not have a simple mental image that captures the full proton. Perhaps no simple image can. The proton is a quantum object, Any picture we use is a compromise between comprehension and truth. Still, pictures are not useless. Imagine the proton as a storm, not because it is literally a weather system, but because the metaphor corrects the most damaging intuition. A storm has structure without being solid. It has boundaries without walls. It persists through motion. It is made from flows, not bricks. It can be stable, while every part of it moves. The proton is far stranger than weather, but the storm metaphor at least points us in the right direction, away from static substance toward organized energy. From this point, the human body becomes almost impossible to see in the old way. Your bones feel hard because atoms arrange into mineral lattices, and electromagnetic forces resist deformation. Your blood flows because molecules interact through fields. Your muscles contract because electrical signals change molecular configurations. But beneath all of this chemistry is nuclear mass, and beneath nuclear mass is QCD energy. You are not only made of star-forged elements, you are made of bound energy from the first microsecond, held in place by a force you never feel directly and yet depend on in every cell. The scale is difficult to hold. A single proton is roughly a femtometer across. A human being is about 15 orders of magnitude larger. A galaxy is another 20 orders of magnitude beyond that. Yet the same small object appears across all of it. Hydrogen protons fill interstellar clouds. Protons burn in stellar cores. Protons anchor water, DNA, rock, air. A universe without stable protons is not merely missing one particle. It is missing the backbone of ordinary matter. This raises the hidden philosophical pressure point of the story. If mass is mostly field energy, then the old materialist comfort of solid stuff at the bottom disappears. But the opposite comfort also fails. We cannot dissolve matter into pure abstraction and pretend physical reality is just thought or metaphor. The proton forces a third position. Reality is physical, but the physical is not what our senses suggest. It is not dead stuff. It is organized activity. It is lawful process. It is energy constrained by symmetry and force into forms stable enough to become atoms, chemistry, planets, and living bodies. This is why the proton is such a good object for a controversy-driven science story. It challenges both the naive realist and the careless mystic. To the naive realist, it says, the world is not built from tiny solid pellets. To the mystic, it says, energy is not a license to abandon precision. The mass of the proton is not a metaphor for consciousness or spiritual vibration. It is a calculable consequence of quantum chromodynamics. The wonder is not that physics becomes vague at depth. The wonder is that physics remains mathematically strict while becoming almost unimaginable. Return now to Einstein's equation. E equals mc squared is often treated as the formula behind nuclear weapons, a symbol of destructive power. But its quieter meaning is more intimate. It says that the mass of a system includes its energy. In a proton, this is not a tiny correction. It is the main event. The equation is not only about converting matter into energy in a bomb or a star. It is about why matter has mass in the first place when the matter is a bound quantum system. The formula is written into your body not as a slogan, but as weight. When you step on a scale, you do not see 70 kilograms of strong force energy. You see a number. You think of fat, muscle, bone, water. Those are real biological categories, but underneath them, nearly all of that mass traces to protons and neutrons. Underneath them, to QCD. Underneath QCD, to fields whose interactions have been running since the early universe. Your body is not only a biological event, it is a long-term storage format for primordial field energy. This sounds grand, and it is, but it is also exact enough to be humbling. The energy in your mass is enormous in principle, but it is not accessible as a human battery. You cannot extract it without nuclear or particle processes of extreme violence. Most of it is locked in by confinement, and confinement is not a loose lid. It is one of the deepest structural facts of the strong force. The energy that makes you heavy is not free fuel. It is the cost of having stable matter at all. This turns the idea of ordinary upside down. Ordinary matter is not simple matter. Ordinary matter is what happens when the universe finds a way to hide extreme energy inside stable forms. The reason you can sit calmly in a room is not because the room lacks violence at depth. It is because the violence is confined, quantized, balanced, and governed. Peace at the human scale is built from storms at the subatomic scale. Think of the early universe again. First a plasma too hot for protons, then cooling, then confinement, then protons and neutrons, then light nuclei, then atoms hundreds of thousands of years later, then stars, then heavier elements, then planets, then oceans, then cells, then nervous systems, then a hand touching a table and asking why it feels solid. The question travels backward through the entire history of matter. The answer reaches almost to the beginning of time. The proton is not merely a component of matter. It is a fossil of an early transition in the universe. Its mass is a relic of the moment energy became locked into hadronic form. Every proton is a tiny archive of QCD becoming cold enough to confine. The fact that these archives are stable is why the universe has continuity. If protons flickered or changed easily, chemistry would have no memory. Matter would not preserve form long enough for complexity to accumulate. There is a deep irony here. The proton is dynamic internally but conservative externally. Inside, constant exchange. Outside, dependable identity. That dual nature makes the world possible. If the proton were internally simple but externally unstable, matter would fail. If it were internally chaotic without law, matter would fail. Instead, it is internally violent and externally reliable. It is a storm that presents itself to the rest of the universe as a stable letter in the alphabet of matter. This is the kind of truth that science sometimes delivers at its best. Not a cheap reversal, but a layered correction. You are not completely wrong to trust your hand. The table is there. The weight is there. The proton is there. But you were wrong if you imagined that there meant solid miniature substance all the way down. The table is there as a pattern of fields. The weight is there as mass energy. The proton is there as a confined QCD-bound state. Reality survives the correction. Intuition does not. The future of this story is not finished. The proton radius has been measured in different ways, and the history of those measurements has included surprises. The distribution of pressure inside the proton, inferred from experimental data and theory, suggests forces of staggering intensity. The proton spin puzzle asks how the angular momentum of quarks, gluons, and their motion add into the proton's total spin. The sea of quarks is not perfectly symmetrical in the simplest way one might expect. Gluons at high energies may form dense states still being investigated. Each new probe turns the familiar particle into a deeper landscape. This should not make the proton feel less understood. It should make our earlier simplicity feel immature. A city is understood at one level by a map of its streets. It is understood at another by its electrical grid, its economy, its language, its memories. The proton is similar, though far more alien. Charge, mass, spin, magnetic moment, radius, Parton distributions, generalized Parton distributions, lattice calculations. Each is a map of a different aspect. No single image is the whole city. And yet, despite the complexity, the proton remains one of the universe's most democratic objects. It belongs to stars and stones, to oceans and blood, to ancient gas clouds and living cells. It is not rare. It is the ordinary miracle repeated beyond counting. Its very abundance may be why we stop wondering about it. We reserve awe for black holes, supernovae, neutron stars, and the beginning of the universe. But the proton carries the same universe inward. It is cosmology folded into the nucleus of hydrogen. The next time you look at a star, remember that starlight is partly the release of nuclear mass energy. The next time you drink water, remember that the hydrogen nuclei in it are protons whose internal energy has endured since the earliest moments. The next time you feel the weight of your own body, remember that you are not weighing static stuff. You are weighing ancient confined energy. You are weighing fields. This does not make life less human. It makes the human body less provincial. We often say we are made of stardust, and that is true for the heavier elements. But there is a deeper sentence underneath it. We are made of proton storms older than the stars that later forged our carbon. The calcium in your bones came from stellar processes, but the mass of the nucleons carrying that calcium comes from a QCD storm, born when the universe was only a whisper of its current age. The body, then, is not a soft exception to physics. It is physics arranged into sensitivity. Every thought you have depends on atoms, whose mass depends on nucleons, whose mass depends on confined energy. Consciousness, whatever else it may be, is not floating above the material world. It is being carried by a material world that is far more dynamic, energetic, and strange than the old word material suggests. A careful scientist would stop before saying the proton reveals the meaning of life. It does not. Particles do not hand us morality. QCD does not tell us what to love, what to build, or how to live. But the proton does reveal something about humility. The thing we call ordinary matter is already extraordinary before biology begins. We do not need to invent magic to make existence strange. We only need to look correctly at what is holding our atoms together. So the central claim returns, sharper now. Matter is not an illusion, and it is not a collection of tiny solid beads. Matter is what energy does when quantum fields bind it into stable patterns. Most of the mass of ordinary matter does not come from the intrinsic mass of its smallest named constituents. It emerges from the strong interaction, from motion and field energy inside protons and neutrons. The strongest counter-argument is that our everyday categories remain valid at our scale. Tables are solid, rocks are heavy, bodies are real. And that counter-argument is right but incomplete. It describes the interface, not the engine. The engine is hidden in every atom. It does not roar where you can hear it. It does not glow where you can see it. It does not announce itself when you touch a table. But it is there, binding quarks, exchanging gluons, generating most of the mass of the world. It is the reason hydrogen has weight, stars have fuel, planets have gravity, and your body can stand upright against the pull of Earth. The proton is small enough to vanish beneath imagination, yet it carries a lesson large enough to disturb the entire human picture of matter. At the bottom of the familiar world, there is no silent pebble. there is no final piece of hard stuff. There is a quantum storm held together by a force so strong that trying to tear it apart only creates more particles. There is energy so densely confined that it behaves as mass. There is motion so stable that it becomes substance. There is another reason the proton resists the small ball image. In a classical object, you can imagine freezing the scene, stopping every part, and still having the same thing. A clock with its gears stopped remains a clock. A bridge with no traffic on it remains a bridge. A proton cannot be imagined that way. Remove the motion and the exchange, remove the gluon field and the quantum fluctuations, and the proton is not a dead proton. It is no proton at all. The identity of the object is inseparable from the activity that sustains it. This is a hard idea because our language is built for nouns. We speak as if the universe is made of things. And then those things do actions. A rock falls. A star shines. A proton contains quarks. But at the scale of quantum fields, the verbs are not secondary. The actions are part of what the nouns are. A proton is not a container in which quarks do something. It is the doing. It is a stable pattern of doing, and that pattern has a charge, a spin, a mass, and a lifetime. Even the word inside begins to strain. We say quarks are inside the proton because scattering experiments reveal point-like constituents within the proton's spatial extent. But these constituents are not marbles floating in a hollow shell. They are quantum degrees of freedom bound into a collective state. The proton has no little metal skin holding them. Its boundary is not a surface like the surface of a balloon. It is a region where the probabilities and fields that define the bound state fall away. The proton is localized, but not walled. The difficulty becomes clearer when we ask about the proton's radius. A school diagram would suggest a neat sphere with a fixed size. Experiments do give us an effective charge radius, derived from how electrons or muons interact with the proton's charge distribution. But even here, the story has been complicated. Different methods once produced slightly different values, creating what became known as the proton radius puzzle. The discrepancy has narrowed, and much has been learned, but the lesson remains useful. A quantum object's size is not measured by placing a ruler against a surface. It is inferred from interactions, and the answer depends on precisely what distribution is being probed. That should make us cautious when we speak about the proton as though it were a tiny bead with a diameter. The proton has spatial structure. It scatters probes in measurable ways. Its charge and magnetization distributions have extent. But it is not a miniature planet. It does not have mountains, a crust, or a center where one could land. It is a quantum-bound state. The closer language always tries to make it familiar, the more it risks hiding the alien nature of the object. One of the most revealing questions is the proton spin puzzle. A proton has spin 1/2, an intrinsic angular momentum that matters deeply for particle physics. When quarks were confirmed, it seemed natural to expect that the spins of the quarks would simply add up to the spin of the proton, but experiments showed that the quark spins account for only part of it. The rest is distributed among gluon spin, quark orbital angular momentum, and gluon orbital angular momentum. The proton's spin, like its mass, is not a simple sum of 3 obvious parts. It is another emergent property of the internal storm. This matters for the central thesis, because it shows a pattern. Whenever we try to reduce the proton to a small list of parts, the proton replies with dynamics. Mass is not just quark mass. Spin is not just quark spin. Structure is not just 3 fixed points. Even momentum is divided among valence quarks, see quarks, and gluons in a way that changes with resolution. The proton is a lesson in humility repeated across observables. The whole is not merely larger than the sum of its parts. The whole defines what the parts can mean. The pressure inside the proton is another startling example. Recent experimental and theoretical work has begun to infer how pressure and shear forces are distributed inside the proton through quantities related to gravitational form factors. The language sounds impossible, measuring something like the mechanical pressure inside a proton without building a tiny pressure gauge. But quantum field theory allows internal stress distributions to be connected to scattering data. The numbers involved are enormous by human standards, a reminder that the proton contains force densities far beyond anything in everyday matter. Again, not a quiet bead, a constrained, pressurized quantum system. And yet the proton is not fragile. This is perhaps the strangest contrast of all. The inner life is violent, but the external identity is stable. Protons survive in the vacuum of interstellar space. They survive inside water molecules, organic compounds, rocks, planets, plasma, and stars. They can be hurled through cosmic space as cosmic rays at nearly the speed of light. They can sit quietly in the nucleus of a hydrogen atom in a glass of water. Their inner complexity does not make them unreliable. It makes them what they are. This is why protons are central to the possibility of a universe with memory. Stable matter is a kind of memory. It preserves structure from one moment to the next. A crystal can persist. A molecule can carry genetic information. A planet can maintain oceans long enough for chemistry to become biology. If the proton's internal storm were not regulated by law, no large-scale order could survive. The small must be reliable before the large can become meaningful. The role of gluons deserves special attention because they are easy to underestimate. Their name makes them sound like glue, a passive adhesive between more important objects. But in QCD, the glue is energetic, self-interacting, and in many ways dominant. Gluons do not simply hold the quarks together. They participate in the structure, carry momentum, generate C-quarks, and contribute substantially to the mass. If the proton is a storm, gluons are not the string tying down the storm. They are the wind, the pressure gradients, the lightning, and part of the storm's substance. This reverses a deep human habit. We tend to privilege objects over relationships. We imagine that the real things are the pieces, and the forces are secondary connections between pieces. The proton tells a different story. The relationships carry energy. The field configuration has weight. The interactions are not optional. They are mass-making. In the strong interaction, the connection is not less real than the connected objects. In a measurable sense, the connection weighs more. This has a philosophical edge, but it remains physics. A proton's mass is not produced by social metaphor or poetic relationality. It is produced by a relativistic quantum field theory with color SU3 gauge symmetry, by quarks and gluons whose behavior has been tested in scattering experiments, collider events, and lattice computations. The poetry is useful only if it serves the mechanism. The mechanism is what keeps the controversy grounded. Consider the phrase pure energy. It appears often in descriptions of the proton, and it can be useful, but it needs discipline. In physics, energy is not a glowing fluid. It is not a substance more spiritual than matter. It is a conserved quantity associated with time translation symmetry in the theories we use. It comes in forms and can be transformed. When we say most of the proton's mass comes from energy, We mean the mass of the bound system includes kinetic and field energy according to relativity. We do not mean the proton is made of vague cosmic light. This distinction may sound cautious, but it is what makes the story stronger. The real result is already astonishing. We do not need to exaggerate it. The proton's mass emerges from QCD dynamics. That alone is enough to overturn the inherited picture. Adding mystical fog would only weaken the discovery. The same caution applies to the word virtual in virtual quark-antiquark pairs. Virtual particles are not tiny classical particles popping into existence like sparks and then disappearing like fireflies in exactly the way animation suggests. They are features of the quantum field calculation, contributions to interactions and fluctuations that can be described in particle language under certain frameworks. The metaphor of pairs flashing in and out of existence can be helpful for a voiceover, but it should not be mistaken for a slow-motion video of little objects entering and leaving a room. The proton sea is real in its measurable effects, but our pictures of it are approximations. This is why a strong science documentary must walk a narrow path. Too much technical precision too early, and the public drowns in formalism. Too much imagery without caution, and the science turns into fantasy. The proton demands both, the violence of imagery and the discipline of qualification. It must feel like a storm, but it must remain a quantum-bound state. It must feel shocking that mass comes from energy, but the shock must remain attached to E equals mc squared and QCD, not drift into metaphor. There is another layer of the mass story often hidden from popular accounts. Mass is not one single concept used the same way in every context. There is rest mass, invariant mass, effective mass, constituent quark mass, current quark mass, binding energy, and mass energy of composite systems. When we say the up and down quarks contribute only a small fraction of the proton mass, we are referring to their small current masses in QCD, not to the effective constituent quark masses used in some models to capture part of the energy surrounding quarks inside hadrons. A constituent quark can behave as if it has a larger effective mass because it is dressed by interactions. This can be useful in models, but it does not mean three heavy little pellets are sitting inside the proton. The distinction between current quarks and constituent quarks is a perfect example of how physics uses different descriptions for different questions. At high energies, in deep scattering, the current quark picture reveals point-like degrees of freedom with small masses. At lower energies, in models of hadron spectra, constituent quarks can be treated as heavier effective objects. Neither description is simply fake. Each is a tool. The error is to mistake a tool for the final ontology. The proton therefore becomes a case study in scientific maturity. Early science often asks what something is made of. Mature science asks which description works at which scale, which quantities are invariant, which are emergent, and which pictures break when pushed too far. The answer, a proton is made of three quarks, is not false. It is incomplete. It names the valence structure, but hides the C, the gluons, the energy, the confinement, and the scale dependence. The better answer is longer, because reality is not obligated to be simple enough for a diagram. Still, the diagram has a role. We cannot teach everything at once. Children learn atoms as little solar systems, then learn that electrons are not planets. They learn protons as little balls, then learn quarks. They learn quarks as little balls, then learn fields. Each step breaks the previous picture, but each picture helped carry the mind to the next. The tragedy would not be using simplified pictures. The tragedy would be refusing to let them break. This is also how the history of matter has unfolded. The four elements broke, the indivisible atom broke, the plum pudding atom broke, the planetary atom broke, the fundamental proton broke. The three-quark cartoon bent under QCD. At each stage, the world did not become less knowable. It became more deeply structured. The breaking of a model was not a defeat. It was the sound of the next layer opening. The proton's mass is one of those openings. For centuries, mass felt like the most primitive property of matter. A thing has mass because it is made of material. Heavier things have more material. That intuition survives in engineering and daily life because it works at large scales. But at the level of nucleons, mass is not just material quantity, it is energy content in a relativistic quantum field system. The old intuition still carries bridges and buildings. It cannot carry the proton. Now imagine removing the proton's QCD energy as a thought experiment. The quarks would retain their tiny Higgs-generated masses, but ordinary matter would lose almost all its mass. Atomic nuclei would not be the same. Chemistry would not be merely lighter. The entire architecture of matter would fail because the strong force does not just add weight. It binds the constituents into nucleons and nuclei. The thought experiment is impossible as a physical operation, but it reveals dependence. The world you know leans on confined energy. What about dark matter and dark energy? They are outside the scope of the proton's mass, and it is important not to confuse them. The statement that ordinary matter gets most of its mass from QCD does not explain the dark matter problem, which concerns gravitational effects on galactic and cosmic scales not accounted for by visible matter. It also does not explain dark energy, the observed acceleration of cosmic expansion. QCD gives us the mass of baryonic matter, the matter of atoms. It is a triumph, but not a theory of everything. This limitation matters because strong claims attract overreach. A documentary voice can say the proton changes how we see matter. It should not say the proton solves all mysteries of the universe. It does not. Gravity remains outside the standard model. Neutrino masses require physics beyond the simplest original version of the standard model. Dark matter remains unidentified. The matter-antimatter asymmetry remains unresolved. The proton is a doorway into one profound answer, not a master key for every locked room. And yet, what an answer it is! The same theory that explains why a quark cannot be isolated also explains why the mass of the proton is so much larger than the current masses of its quarks. The same self-interacting gluons that make QCD hard to calculate also make the proton heavy. The same confinement that prevents us from pulling out a quark stores the energy that becomes mass. The difficulty and the answer are the same thing. This has a strange emotional consequence. We often imagine the fundamental level as simpler than the world above it. Biology is complex, chemistry simpler, atoms simpler, particles simplest. The proton disrupts that latter. A living cell is more complex in organization, of course, but the proton is not simple in the way a child's hierarchy suggests. Going smaller does not always mean going simpler. Sometimes it means entering a regime where the basic rules are fewer, but their consequences are more mathematically fierce. This fierceness is why experiments are still needed. Theory alone does not tame the proton. Scattering experiments map how quarks and gluons share momentum. Collider data tests QCD across energy scales. Heavy ion collisions explore deconfined QCD matter. Precision spectroscopy helps refine proton structure. Lattice calculations connect equations to masses. Future facilities aim to image the proton in new ways, not as a photograph, but as a multi-dimensional map of momentum, position, spin, and gluon density. The word image will always be imperfect. You cannot take a normal picture of the inside of a proton. A picture requires light, and light at the needed wavelength would itself be an energetic probe that changes the system. Instead, physics builds images from interactions. It throws known questions at the proton and reconstructs structure from the pattern of answers. This is not a weakness. This is how the invisible becomes scientific, not by being seen directly, but by producing consequences no other model can explain. There is a quiet drama in that method. We cannot touch the proton's interior with a finger. We cannot watch gluons with an eye. But we can infer, calculate, collide, scatter, compare, and refine. Human beings, made of protons, build machines to interrogate protons, then use the answers to discover why human beings have mass. This is science at its most recursive. Matter asking matter what matter is. The recursion should not be missed. The same strong force energy that gives your body mass also gives mass to the detectors, magnets, wires, shielding, and silicon sensors used to study the proton. The instruments are made of the phenomenon they investigate. The equation being tested is written into the laboratory walls. The experiment is not outside nature looking in. It is one arrangement of nature forcing another arrangement to reveal its rules. This is why the final image cannot simply be a proton in isolation. The proton story runs through the history of human knowledge. It runs from ancient philosophy to chemical ratios, from cathode rays to gold foil, from particle zoos to quarks, from SLAC to CERN, from blackboards to supercomputers, from the early universe to the atoms in your hand. Every stage adds a correction. Every correction makes the familiar world stranger and more exact. There is also a moral of method here. The strongest ideas in this story survived because they risked being wrong. The quark model made predictions. QCD explained asymptotic freedom. Deep inelastic scattering revealed point-like constituents. Lattice QCD produced masses that could be compared with measurements. The Higgs mechanism predicted a particle that took decades to find. These are not vague claims protected from refutation. They are sharp structures tested against the world. That is why this subject can carry a controversial thesis without becoming pseudoscience. The controversy is not that secret energy proves matter is fake. The controversy is that the ordinary concept of matter, the one built into common sense, fails at the very place where we expected it to become simplest. Physics does not replace the world with fantasy. It replaces naive solidity with lawful emergence. Lawful emergence may be one of the deepest ideas in modern science. A proton's mass emerges from QCD. A nucleus emerges from protons and neutrons, bound by residual strong force. Chemistry emerges from electron structure. Biology emerges from chemistry. Consciousness may emerge from biology, though the full story remains open. At every level, new properties appear that are not obvious from the parts viewed separately. The proton is not a mere example of emergence. It is the foundation on which many later emergences rest. The word emergence can sound soft, as if it means we do not know what is going on. But in QCD, emergence can be hard and quantitative. Calculate the fields correctly, and the mass appears. The proton's mass is not put in by hand as 938 mega-electron volts. It comes out. That is the difference between mystery and mechanism. The result is surprising, but not ungrounded. Perhaps the deepest shift is this. Mass is not necessarily a primitive input. In ordinary matter, it is largely a result. the result of confinement, the result of relativistic energy, the result of quantum fields interacting in a stable way. A thing can weigh something not because its ingredients individually weigh that much, but because the system's energy does. The whole does not merely exceed the sum of its parts poetically, it exceeds them in kilograms. This fact should echo through the way we speak about ourselves. We are not just atoms, if that phrase means simple dead beads. Atoms are already layered achievements. Nuclei are already strong force architectures. Protons are already storms. To be made of atoms is not to be reduced to something dull. It is to be assembled from processes whose depth we are still learning to describe. But humility cuts both ways. Being made of proton storms does not make us supernatural. It makes us natural in a universe where nature is stranger than the supernatural stories we once invented. The awe belongs to the physics itself. No extra miracle is needed. The strong force, the Higgs field, quantum mechanics, relativity, cosmic history. These are enough to make a human hand mysterious without making it magical. So when we say the mass you feel is energy, the consequence is not that you should doubt the world. The consequence is that the world is more unified than it appears. The fire of a star, the binding of a nucleus, the weight of a stone, and the equation on a chalkboard are not separate domains. They are different expressions of mass energy and field dynamics. The same principle that powers sunlight helps explain the heft of the particles that make you. The proton is small, but it refuses to stay small in meaning. It touches the early universe, the birth of matter, the burning of stars, the periodic table, the stability of atoms, the weight of bodies, and the limits of human intuition. It sits at the crossing of the very large and the very small. Cosmology enters through its age. Quantum field theory enters through its structure. Human experience enters through touch. If the documentary began with a hand on a table, it ends with the recognition that your hand and the table are not opposites. They are two temporary arrangements of the same deep principles. Their electrons repel, their atoms hold, their nuclei carry protons and neutrons, and those nucleons carry ancient confined energy. The contact between hand and table is a meeting of two field architectures, each supported by storms hidden beneath the threshold of sensation. There is comfort in that, but it is not the comfort of simplicity. It is the comfort of coherence. The universe does not have to match our intuitions to be intelligible. It only has to obey rules stable enough for minds to discover them. The proton does not look like common sense, but it obeys a mathematics that has allowed human beings to predict, test, and calculate. That is a deeper kind of order than the order of familiar pictures. And perhaps this is the final lesson. The world did not become less solid when we discovered atoms were mostly empty. It became more beautifully supported. Matter did not become less real when we discovered proton mass is mostly energy. It became more deeply unified. The proton did not become less of a building block when we discovered quarks and gluons. It became a building block with a history, an interior, and a storm powerful enough to give weight to the visible universe. There is one more subtle point before the final return to the hand and the table. The proton teaches us that explanation does not always mean visualization. Human beings are visual animals. We want to see a thing. We want a shape, a boundary, a little machine with parts that move in ways we can imagine. But quantum field theory often gives us something better and less comfortable, a structure of predictions. It tells us which quantities can be measured, how they relate, how they change with energy, and how they emerge from symmetry. It may not give the mind a clean picture, but it gives the experiment a number. This is why the proton is both intimate and remote. It is intimate because you are made of it. Remote because the most accurate description of it is not an image, but a theory. You cannot see color charge. You cannot watch a gluon split. You cannot point to a C quark the way you point to a pebble. What you can do is measure scattering patterns, compare cross-sections, calculate on lattices, observe jets, test some rules, and watch the same framework survive again and again. The proton becomes real not by resembling common sense, but by resisting every attempt to replace it with something simpler. The same thing happened with the atom. No one saw an atom directly when atomic theory became powerful. Chemists trusted ratios. Physicists trusted Brownian motion. Later instruments made atoms visible in specialized ways, but the theory had already earned its place through consequences. The proton's interior is similar. We do not need a literal photograph to know it has structure. Its structure is written in how it responds when struck by electrons, photons, muons, neutrinos, and other hadrons. Reality leaves fingerprints before it shows a face, and the fingerprints tell a consistent story. The proton has a valence identity, 2 up quarks and 1 down quark. It has a C, quark-antiquark pairs, and gluons, contributing to momentum and structure. It has confinement, no isolated color charge. It has asymptotic freedom. Quarks behave more freely at short distances. It has mass mostly from QCD dynamics. It has a spin assembled from several internal sources. It has distributions that change with probing scale. No single one of these facts alone gives the whole proton. Together, they form a portrait that is stranger than any illustration. A careful observer might still ask whether energy gives mass, merely moves the mystery. Why does energy gravitate? Why does a field configuration resist acceleration? Why is E equals mc squared true? At that point, the answer must go deeper into relativity and the structure of space-time symmetries. The documentary cannot solve all physics at once, but it can mark the boundary honestly. The proton's mass is explained within the framework of relativistic quantum field theory. That framework itself rests on deeper principles still being explored, especially where quantum theory and gravity meet. Science is not a stack that ends in total comfort. It is a widening set of reliable relations. The reliability is enough to change the world. Nuclear energy, particle accelerators, medical imaging, radiation therapy, semiconductor technology, precision clocks, and astrophysics all depend on the same revolution in understanding matter. The storm inside the proton is not a decorative truth. It is part of the reason the 20th and 21st centuries could build machines that probe the early universe, treat cancer, and measure particles that live for less than a trillionth of a second. Abstract physics becomes infrastructure long before most people notice. This is why the proton story belongs in a space science documentary rather than only in a particle physics lecture. Space is made visible by matter. Stars shine by nuclear rearrangement. Galaxies glow because atoms form, cool, collapse, and fuse. Planets exist because nucleons have mass, and chemistry has stability. The cosmic story is not only about vast distances, it is also about the microscopic conditions that make vast structures possible. A galaxy without stable protons is not a galaxy, as we know it. A star without nuclear binding is not a star, as we know it. A planet without atoms is not a planet. The large depends on the small more completely than intuition admits, and the small depends on laws that seem almost tuned against simplicity. The strong force must confine, but also allow short-distance freedom. Quark masses must be small, but not irrelevant. The neutron must be slightly heavier than the proton, but not by too much. Nuclear binding must allow hydrogen to burn, helium to form, carbon to exist, and heavier elements to be forged. We should be cautious about turning this into a claim that the universe was designed for us. Physics has many ways to warn us against easy teleology, but we can say this: the fact that complexity exists depends on a narrow cooperation between constants, fields, and interactions. The proton sits near the center of that cooperation. This gives the controversy its final shape. The common view says matter is made of tiny things, and those tiny things give matter mass. The stronger scientific view says ordinary mass is largely emergent from energy in quantum fields, especially the strong interaction inside protons and neutrons. The counter view warns that we must not turn emergence into illusion or energy into mysticism. The synthesis is more powerful than either extreme. Matter is real because fields form stable energy-bearing patterns, and those patterns can be measured, calculated, and trusted even when they defy our images. That is why the proton is not merely a correction to school diagrams. It is a correction to the way we imagine reality's foundation. The foundation is not a floor of little stones. It is an activity that holds, a process that repeats, a storm that remains itself. The visible universe rests not on inert substance, but on stable motion. Place your hand again on the surface near you. Nothing has changed. It still feels solid. It still pushes back. It is still safe to call it a table, a wall, a chair, a hand. Science does not take that world away. It deepens it. Beneath the surface, beneath the atoms, beneath the nucleus, beneath the old diagram of three quarks, the storm continues. It was there before Earth. It was there before the sun. It was there before the first star ignited. It has been burning without flame since the universe was a microsecond old. And now, for a brief moment, that storm has arranged itself into something that can know it is a storm. The energy inside the proton became atoms. Atoms became chemistry. Chemistry became cells. Cells became nerves. Nerves became thought. And thought turned back toward the proton and asked what matter is. The answer is not simple. It is better than simple. You are not made of solid little things. You are made of ancient energy, bound by fields, stabilized by law, shaped into matter by the strongest force in nature. Your weight is the weight of confinement. Your body is a temporary architecture built from storms that may outlive the stars. And the most famous equation in physics is not only written in textbooks or carved into the history of nuclear fire. It is written quietly into every proton in your body. E equals mc squared is not just a formula about what matter can become. It is a clue to what matter already is.